After the complexities of acceleration in a circle, the derivation of force is very straightforward. Newton's second law tells us that force and acceleration are directly proportional, with the constant of proportionality being the mass of the object. It gives us the equation force equals mass times acceleration. The same is true for circular motion. There is no complexity or difficulty. The force pulling an object to the centre of a circular path that the object is travelling is equal to the mass of the object multiplied by the acceleration that the object is undergoing. The force always acts towards the centre of the circular path, and the magnitude is always equal to mass times acceleration. In circular motion, we are fortunate because we have two ways of representing acceleration, which we showed in the previous podcast. Size of acceleration. We can state centripetal acceleration using angular speed of an object, the speed at which an object uses up angles around a circle. Or we can show centripetal acceleration as a consequence of the tangential velocity of the object, the velocity the object would achieve if the force were removed suddenly. Using angular speed, our equation for centripetal force is centripetal force equals mass multiplied by angular speed squared times by the radius of the circle. Using tangential velocity, our equation for centripetal force becomes centripetal force equals mass multiplied by tangential velocity squared divided by the radius of the circle. Both of these equations give identical answers, but can be used when you have either angular speed or tangential velocity. They are also exactly the same as the equation for Newton's second law, except we have gone into more detail about how to give the acceleration in a circle. We could have done something similar for linear motion if we had stated that force is equal to mass multiplied by velocity divided by time or speed divided by time. We chose not to.